Hello everyone, I enjoy taking videos while walking with GoPro hanging around my neck, since I bought GoPro 9 in 2020. On this video, I am going to provide you interesting GoPro Motion animation with some mathematical treatments. GoPro Motion animation is created using metadata included in MP4 video file. The video you are watching now is one of my favorite parks, Kasai Rinkai Park located in Tokyo Bay Area, Japan. GoPro animation in the lower left, violet colored, is called Real GoPro, which shows GoPro body attitude and vibration detected by gyroscope. The green animation in the lower right shows GoPro Motion as the screen is cropped by the GoPro's electronic anti-shake function. For example, if the GoPro body momentarily turns left due to camera shake, it turns right. I call it cropping GoPro. These two data are included in the metadata of MP4 file. The yellow one in the lower middle is virtual GoPro. This represents the attitude and orientation of the GoPro aligned with the image after stabilization. In other words, it represents the movement of real GoPro, minus the camera shake. Also, you can see that the vibration is not only removed, but the movement is kind of slimy. Virtual GoPro data is not included in the metadata. Later, I will show you how to make it from the existing data. This is the outline. In Chapter 1, I am going to talk about GoPro animation, especially virtual GoPro. In Chapter 2, I am going to talk about gyroscope offset compensation. Because of the offset, the baseline of real GoPro and virtual GoPro gradually tilts over time. The attitude and orientation of the object in motion is obtained by time integrating gyroscope data, namely angular velocity. Since the angular velocity includes some offset, the offset component accumulates when integrating and then the baselines are tilted over time. I will introduce three methods to compensate and correct the offsets. The first two are well known. Especially, sensor fusion method is an important technology in everyday use such as smartphone. The third one is just my original idea. It's not so precise, but simple. It's good enough for my GoPro animation usage. In Chapter 3, I am going to talk about how to differentiate the quaternion to the angular velocity. When we correct the angular velocity offset, the angular velocity data are required. In case of virtual GoPro, there are originally no angular velocity data. That's why we need to differentiate the quaternion. Generally speaking, time differential of the quaternion is not so familiar as time integral. Let's get started with virtual, real, and cropping GoPro animation. GoPro metadata are easily extracted for free at this website. Click Free button, and drag and paste the MP4 file on Choose File. And then, it starts reading the file. Click More Streams to expand the menu. Select the stream you want, for example, camera orientation. On the left side menu, at the option, Frequency, select Frame Rate. This is very important when you make the data synchronize with video. On the right side, you can select Output File Format. I usually use CSV file. Both Excel and Python are available. In case of GPS data, GPX file format is more convenient when inputting on Google Earth Pro. The download completed. Here, let me introduce the metadata included in GoPro 9 and 10. This table shows the metadata I frequently use. Neither GoPro 10 nor GoPro 9 has any E-compass, namely, magnetometer. GoPro Max, 360-degree camera is available. CORI and IORI are composed of quaternions which make real GoPro and cropping GoPro respectively. Real GoPro can be also obtained by integrating gyroscope, namely angular velocity. Contents of main CSV files are shown here. CTS at the first column shows the time count and its unit is milliseconds. Basically, each line is expressed every 33.3 milliseconds, the frame rate. The most interesting metadata is gravity vector, which is originally derived from the accelerometer. It shows the direction for gravity, where the component due to the acceleration motion of the object is removed and the magnitude of the vector is normalized to 1. As mentioned later, the sensor fusion calculation uses this gravity vector, not the accelerometer. Now, let me explain how to create virtual GoPro. The quaternion of virtual GoPro is given as the quaternion product of cropping GoPro and real GoPro. The quaternion product is not commutative mathematically. PQ does not always equal QP as shown in the definition. Later, I will show you the result of the reverse product on the video. This graph shows the quaternion of real GoPro, camera orientation of the video at the beginning. Vertical axis is the 4 elements of the quaternion. Horizontal axis is elapsed time of the video. Its unit is seconds. You can see small vibration on the line. It's due to camera shake. This graph shows the quaternion of cropping GoPro, image orientation. You can see small vibration as well. This graph shows the quaternion of virtual GoPro. This is a result of quaternion product of cropping and real GoPro. You cannot see any small vibration on the line. I cut all of spike anomalies numerically like this. I tried to calculate the reverse product. Q1 and Q3 have bigger vibration than original real GoPro. It's kind of strange, but no meaning mathematically. Let's see the video again. This time, the reverse product of real GoPro and cropping GoPro is also overlaid. The basic orientation is similar as virtual GoPro, but small vibrations still remain. Here is a Python code making GoPro animation for reference. Using plotter method of PyVista module, you can create the animation. GoPro model data, STL file was obtained from the net, and simplified. This line shows the quaternion product. This hash-marked line shows the reverse product. Next, let's get started with gyroscope offset compensation. Before telling the story, look at this picture. It was copied from GitHub site. IMU stands for Inertial Measurement Unit. It is an accelerometer and gyroscope sensor unit mounted in GoPro. My calculation follows this notation. This video lets you know how important the gyroscope offset compensation is. This is Uchibori Dori Street near the Imperial Palace, Tokyo. It's one of the most popular jogging trails. I am walking with GoPro hanging around my neck, looking straight ahead on the straight road without losing posture. Even if there are some vibrations accompanying my walking steps, both real GoPro and virtual GoPro baselines should be kept horizontal. But the baselines are gradually tilting, because of the gyroscope offset. Let's compare the beginning and the ending of this video. Video duration is less than 70 seconds. You see that this phenomenon is serious in creating GoPro motion animation. That's why I tried to correct this phenomenon. Here, I will provide you 3 methods. Sensor fusion, static state recording, and coinciding attitude at the start and end. In sensor fusion, I adopt the extended Kalman filter, which is the most familiar tool in this field, and has been featured on so many websites. My video doesn't mention the theory, just says how to do it. I calculated the several cases shown on the table. As mentioned at the beginning, GoPro 9/10 has no E-compass. Here, instead of sensing by E-compass, the Earth's magnetic vector is virtually generated. The detail will come later. In 9-axis, I use that value in order to check the Python code. Here's a conventional algorithm of the extended Kalman filter. The keywords are state variables, transition equations, measurements and observation model. Once you have fixed them, all you have to do is code according to the algorithm. It's an example for reference. In this code, the axis number is 9-axis and the state variables are composed of quaternion and gyroscope offset. Here, it reads virtually generated Earth's magnetic vector. And gravity vector is used instead of the accelerometer as mentioned before. These lines show repetition of the extended Kalman filter. If you import NumPy module on Python, matrices can be treated as variables. If you want to calculate 3-axis, then set Kalman matrix, K0 matrix. Here are state variables, transition equation and its Jacobi matrix. On the Python code, the transition equation and its Jacobi matrix are defined as functions. This slide shows how the observation model H is constructed. All you have to do is do sandwich product with respect to gravity vector 0, 0, 1 and the Earth's magnetic vector at the place, using the quaternion coordinate rotation system. As a result, we got observation model H and its Jacobi matrix. On the Python code, observation model H and its Jacobi matrix are also defined as functions. Finally, initial values. Just examples. In case Euler angles are used as the state variables, it looks like this. Functions defined on the Python code look like these. Finally, initial values. Just examples. This slide shows how to create virtual Earth's magnetic vector. The concept is the same as the observation model mentioned before, using the quaternion coordinate rotation system. The calculated results come later. Now let's take a look at results. The previous video data taken near the Imperial Palace are used here. The expression by x on the upper right of the graph shows the state variables used in the calculation. The results are expressed by Euler angle notation. The unit is degrees. This notation is easier to understand than the quaternion notation in this case. If the gyroscope offset is ideally 0, the pitch, roll and yaw baseline should be flat, not tilted. This result shows 3-axis case, namely without sensor fusion. The baselines are tilted 10 to 30 degrees for 70 seconds, as you saw the previous video. This result shows 6-axis case. You find that pitch and roll baseline get flat, but yaw baseline is still tilted. In case of 6-axis with accelerometer or gravity vector, the offset related to yaw angle cannot be fixed. On the Python code, I added an appropriate offset value on Z component of the gyroscope and then the yaw baseline got flat. In this situation, next to do is generate the virtual Earth's magnetic vector as mentioned before. The obtained result is like this. Using this data, I can calculate 9-axis case. This is a 9-axis case. The state variables are only 4 elements of the quaternion. The roll baseline gets flat, but the pitch and yaw baseline are still tilted. I will discuss it later. This is also a 9-axis case. The state variables are composed of 4 elements of the quaternion and 3 elements of gyroscope offset. As a result, this time, all the baselines got flat. Next, the state variables are Euler angles. Even if there are no gyroscope offsets, all 3 baselines got flat. This is my consideration for the results obtained so far. First, suppose that the state variables are composed of 4 elements of the quaternion. In 6-axis, the pitch and roll baseline are corrected under the condition that the gravity is parallel to the z-axis of the world coordinate. In 9-axis, in other words, by adding magnetic sensor condition, the pitch and yaw baseline are disturbed due to the excess measurement condition. If the gyroscope offsets are added on the state variables, they could work as an adjustment margin. On the other hand, in case of Euler angle state variables, there are no excess measurement conditions existing. Next, let's talk about the static state recording. This method is very simple. Right after walking in the previous video, I just kept GoPro still and recorded for 90 seconds as you see. The obtained angular velocity is like this. The unit of the vertical axis is radian per seconds. You see that the average is not 0. I set each average value as the offset. This is the quaternion during static state recording. This shows Euler notation during static state recording. On the Python code, 3 offset values are manually input, and then calculated. This shows quaternion notation. This shows Euler angle notation. In this method, it is assumed that the offset drift is negligible during recording against your allowed accuracy. It is well known that gyroscope offset value changes with temperature and time. So static state recording should be done right after or right before the actual recording. The final method I came up with by chance. This method requires special camera work. It is to coincide the GoPro body attitude when starting and ending the recording. Assuming that the difference of the attitude between start and end is negligible, each axis offset value is given like this. Here, delta t is record duration, its unit is seconds, and q1, q2 and q3 value at the endpoint are required to calculate the offset values bx, by, and bz. In order to reduce the vibration when pushing the star button, voice control, or smartphone control, remote controller is recommended. In addition, you don't have to go back to the start point. At the start point and the end point, you may aim for distant landscape. This is the original quaternion and each offset value is calculated using the endpoint value of q1, q2 and q3. And then recalculate. You see q1, q2 and q3 baseline gets flat. By Euler angle notation, all 3 angles are flat, as well. I just summarized the gyroscope offset compensation on the table. The gyroscope offset including its drift is said to be determined by individual product differences. Many IT such as smartphone adopt sensor fusion algorithm. In the last chapter, I am going to talk about quaternion time differentiation to angular velocity. Here, I will introduce 3 methods. Solving simultaneous equations, quaternion operation on Python and using Python function in quaternion module. The data used in this chapter is the same as the video at the beginning, taken at Kasai Rinkai Park. Let's get started with the basic formula. Q dot equal on half, omega, Q. Omega and Q are given like these matrices. Discretize this, and express as a matrix, it looks like this. Expanding the matrix yields 4 equations. There are 3 unknowns, x, y, z component of the angular velocity omega. Though the number of equations is 1 more, by selecting any 3 equations, the final result is the same. However, depending on which of the 3 equations you select, the angular velocity expression will be different, and the quaternion element in the denominator will change, as you can see. In order to identify the cases, I name them according to the quaternion of the denominator, such as denominator Q0. As you can see, the expression for the actual angular velocity is a huge number of polynomials. I dared to list the formulas for comparison with the calculation of the quaternion operation that will appear later. I compared 4 cases using the y-axis component of the angular velocity. In denominator Q1 and Q3 cases, the calculated results are very noisy. As you can see, the quaternions Q1 and Q3 are nearly 0 for most of the time. Probably, the numerical calculation error increased because both the denominator and numerator are approaching 0. Therefore, the solution of the case where the absolute value of each element of the quaternion is the largest is adopted, and then the calculation results are connected. Here, the calculation results of the denominator, Q0, and the denominator, Q2, are connected. There does not appear to be a large angular velocity discontinuity at the connected parts. You can see there are so many spike anomalies. Spike anomalies are accumulated when the angular velocity is integrated over time, so they should be taken care of. I cut the spike anomalies up to the root, as you can see. For reference, it is my program code of removing spike anomaly. Next is how to process with quaternion operation. The basic formula to start with is also the time derivative of the quaternion Q dot equals 1/2 omega Q. Here, the contents of omega matrix are compared to the quaternion product definition, where P can be replaced with omega, and the angular velocity omega is a quaternion with 0, omega x, omega y, and omega z as components. Finally, the basic formula can be expressed like this. The tilde above a letter is often used to indicate that the letter is a quaternion. Discretizing this formula, it is possible to code on Python. The actual Python code is like this. If you install the quaternion library, you can handle the quaternion as a variable. Quaternion operation is much easier to work with comparing to the previous method of solving simultaneous equations. Calculation result, here. Next, let's calculate using the angular velocity contained in the Python quaternion library. The argument is an array of quaternions and the corresponding time array, and the return value is an array with angular velocity having x, y, and z component. Since the function definition is described on GitHub site, I will introduce it. The package called scipy is used to calculate the time derivative r dot of the quaternion. Angular velocity calculation is described in the return statement. What caught my attention was r./r. There are 2 rotation systems in the quaternions. The position vector rotation system and the coordinate rotation system. The results will be different depending on which system you are discussing. The order of the quaternion product in the basic formula is different. Python's angular velocity function seems to adopt the former. My calculation adopts the latter. As you can see, I checked the contents of the function outside. Of course, r./r has the same calculation result as original function. I calculated 1/r by r dot by changing the order of the quaternion product. This is the result of the comparison. I found that by changing the order of the quaternion products in return statement, the result matched my previous data. These are 3 graphs obtained. There is no big difference among those. By the way, Matlab has a similar function as well. The rotation system is selectable with the argument. Now let's watch the video again. All 3 above are virtual GoPro. The angular velocities were integrated to the quaternion. As you can see, the first and second calculations are mathematically equivalent. Considering the coding complexity, Quaternion operation is a more elegant and reasonable way to do computations than solving simultaneous equations. Except the rotation system of the quaternion, the difference between my calculation and Python function is the time derivative of the quaternion, q dot. In my calculation, q dot is the quaternion subtraction for each element divided by the time difference. Actually, I am not sure what the quaternion subtraction means mathematically. On the other hand, Python function use interpolation and derivative. As far as I checked, there is no big difference between both. Finally, we found that the quaternion can be transformed to the angular velocity. By going back to the angular velocity, we are able to compensate the gyroscope offsets of virtual GoPro, which are derived from the quaternion product of cropping GoPro and real GoPro. Thank you for watching.